video is for the accuracy of linear function models correlation coefficient. So today again, excuse me, we're determining how accurate our linear models are. Today we're going to use what's called the correlation coefficient. So the correlation coefficient, also known as the R value, is the numeric value that assesses the strength of the linear relationship between two quantitative variables in a set of bivariate data. So the greater that our correlation coefficient, our R value, is to 1, either negative or positive, again, the straighter the line is going to be, the closer to 0 is there's not a relationship, or there's not a linear relationship there. So the range of the correlation coefficient is -1 is less than or equal to R is less than or equal to +1. So anything from 0 to -1, this is a negative correlation. It means that our data has a negative trend. It's going downhill if we would graph it on a scatter plot. The closer we are to 0, it gets weaker, and the closer that we get to 1 makes it stronger. So if your correlation coefficient is a -1, that is a strong negative correlation. 0 correlation means there's no association there. There looks like a bag of marbles thrown on the floor. And then again, so from 0 to +1, this is a positive correlation. And again, the closer we are to 0 is weak. Closer that we get to +1 would be a stronger, so a +1 would be a strong positive correlation. All that data almost lines up perfectly and in a nice, pretty straight line. All right, so the table shows the population of Wichita Falls, Texas for each decade between 1900 and 1960, determined using rate of change. The function p of x equals this function. Could model the population data where x is the decade since, that should say 1900, woo, and p of x is the population of Wichita Falls. All right, so what we're going to do is we're going to take this actual data and we're going to determine a linear regression function. So this is using the average rate of change. So using linear regression, all right, we're going to go to list and spreadsheets. A is X, B is Y. And we're going to put our data in. Make sure everybody matches up nice and neat. Okay, once you get your data in, it's going to be menu 4, 1, and then 3 for linear regression. Our X list, we labeled X. Our Y list, we labeled Y. And then these values here, so you can see M, here's my slope, here's my y-intercept. So I can write an equation. Y equals 15085.3x minus 1063.54. That, using linear regression, is the equation that I get. Determine the correlation coefficient. That is this number here, just the R. We're going to round it off to 2 numbers after the decimal. So R equals 0.96. Now, for this notes, or for these notes, this is quite a chunk of writing to do, so I'm going to pull up the answer key so you can pause your video, write it down, and then we'll discuss it. Okay, so again, you can pause your video here to write this information down here. But it asks, is P of X a reasonable linear model for this data? Is my average rate of change, so, or not my average rate of change, is the linear regression model accurate? So the correlation coefficient, that's this value, indicates the linear regression equation has a very strong linear correlation, very strong positive for the given data. The constant term and coefficient are not reasonably close in value. Okay, so not only do we have to look at this, we also need to look at, let me go back to this screen. We also need to look at these values. We need to match these values up. So this is 15,000, this is 16,000. So those are close. But then if we look at our y-intercepts, here the y-intercept is positive 2,500. Okay, means I start at 2,500. That's an accurate y-intercept, starting at 2,500. Again, this is the real world data. Doing it mathematically though, it says we should start out at a negative population, and that's not really a reasonable or feasible thing. Towns don't start out at a negative y-intercept. So again, if you need to go back and pause the video to get that answer key, you're more than welcome to do that. Okay, so we've got another set of data here. The table shows the population of Wichita Falls, Texas for each year since 2016. Determined using rate of change, the function Q of X equals, so this function could model the population data where X is the year since 2016 and Q of X is the population of Wichita Falls. So just to kind of rephrase what I said earlier, we're determining the accuracy of this model here, not of this one. I phrased it backwards, so I apologize for that. So what we're going to do is we're going to do linear regression on this table. So we've already done one set, so what I'm going to do is I'm going to X out of this. I don't want to save it. I want to start nice and fresh and clean. So up there next to A, we put an X, B, we put a Y, put our X values in, and then we can put our Y values in. Okay, menu 4, 1, 3. And I will be giving you a notes handout, a calculator tip page that lists all these steps so you have something that you can go back and reference to do this. Okay, so here we have, and we're going to round off. We're going to round off a little bit here. First time I did this, my numbers were a little bit different, so I'm just going to go with my original. So my linear regression the first time I did this was 265.786x plus 103,981. My R value, if I come down here and I round this off to 2 numbers after the decimal, my R value, 0.99. So this data is very linear. It is a positive association, a positive trend. And then the other thing we look at, we match these values up. So here we've got 264, if we round it, 265, that's almost on the nose. Here we've got 104,000, here we've got 103,000, but again, if we round that up, it's going to round to 104,000. So my coefficients are extremely close. My y-intercept, my constants, are extremely close. So again, I'm going to pull up this answer key for you. You're more than welcome to pause this video right now if you want to write, or you need to write this information down, and then we can discuss it. But the correlation coefficient indicates the linear regression equation has a very strong linear correlation for the given data. We talked about the constant term and the coefficient are reasonably close in value. And so in this case, Q of X is a reasonable model.